What I want to look at here is something called momentum, and people, up to the stage may have used the expression sometimes, but you now need to know exactly what it is, and it's quite easy to define. It's mass times velocity, and the symbol we give it is P, and mass is just a number, right? V is velocity, so that is a vector. So if you multiply a vector by just a number, you got another vector. So momentum also has a direction. So if this was your velocity vector and you then multiply it by mass, and mass is greater than 1, then you'll end up with a new vector, p, going in the same direction. And that's momentum. And at this stage you're going, wow, much to that really, is it? But the whole thing about momentum is we've got something called conservation of momentum. And this is one of the most important principles in physics. It's just about, if not more important than conservation of energy. So we use it in a lot of examples. We say that momentum is conserved. It's a law of the universe. Conserved means you can't lose the overall momentum in a situation. Now, there's a few sort of conditions there. One is conservation of momentum acts as long as there are no outside forces acting. And that's because forces will change momentum. That's exactly what a force does. If momentum equals mv, then if v is changing over time, that's an acceleration, then to have that happen implies that we need a force. So no outside forces acting is one of the main conditions for conservation of momentum. So when you have a system, let's change sheets here. You have to sort of define your boundaries and say, okay, this is my system. It's an enclosed system, isolated system if you like, and there are no external forces acting. Could be a whole bunch of gas molecules all racing around doing their own thing like this. Right? Now the point is, all these little guys are smacking into each other, right? And when they smack into each other, they exert forces on each other. But there's always going to be equal and opposite forces. So when this one hits that one, it might cause a force on that one, like that. There's going to be an equal and opposite force on that one. So there will be a change in momentum on this little guy, but there'll be an equal and opposite change in momentum on the other guy. So if we're adding up, if we added up all the momentum, if we could stop time and we added up all the momentum here, we would have a total momentum. And no matter how much these little guys smack into each other, they're never going to lose that total momentum. They'll change their momentums, but they're sort of like swapping little bits of momentum. And remember, that momentum's just not a speed, it's directions too. So to add up all the momentums, you would have to add up all the little vectors in the whole system. And can you imagine this little chain of vectors for millions and millions of atoms? But it would be in 3 dimensions, right? And you'd end up with this overall arrow representing the total momentum. And that wouldn't change as long as there are no outside forces. So that's the interesting thing. Momentum's quite cool. What we'll do, I think, we'll stop that one there and we'll do an example where we, a one-dimensional example of momentum.